Welcome to YMT215 Logic Circuits. Today we are going to discuss the second part of Chapter 3, Logic Gates and Gate Combinations. Previously we studied just an introduction to Boolean algebra, and we understood the point of learning such an algebra and where and how it is applied. So today let's go ahead and discuss the gates, where we exactly apply this Boolean algebra along with other operations. Right, so today we'll discuss all the gates, the common gates that we are going to use or build circuits with them, and speak a little bit about programmable logic at the end. NOT gate. We explained about NOT gate before, but let me just revise what we said. It does the complementation job or task. That means if you place 1, it will produce 0, or if you place at the input, of course, if you provide or feed 0, it will produce 1, and that's what it does. How do we draw it? What kind of symbol it has? It has this triangle with a bubble, and this is the famous, actually, or most commonly used symbolic diagram of a negation or NOT gate. And we have two versions of this. The first one, the bubble at the end, or at the output, or at the beginning, or at the input side. And I'll explain the difference between these two in a while. Now we have another symbol represents the NOT gate. You may find it in other books or wherever you may refer to logic circuits while you are reading. This is exactly a rectangular shape with a triangle at the output or at the input, which refers to the negation process, and we have here 1 referring to NOT gate with 1 input, and NOT gate accepts only 1 input and produces only 1 output, and that's it for the negation. Now the bubble, I said I'll explain about it, the difference between the one at the output and the one at the input, which applies to these two, is what we refer to by active low at the output or active low at the input. Active low means what? It means that what will be changed here or activated or activate the output here is a low input. Why? If you provide 0, we will get an output 1. This is what we call activating. If we provide 1 here, the output will be 0. So it will be activated while it is low. Low output will be active in that case. 0 bar will be active in that case. That is what we refer to by, and this is what is written here. I just summarized it. Active low at the output produces 0. That means it should be activated in an inversion or negation process. Active low as an input, 0. That means if you provide 0 or whatever that produces 1 at the output will be given is the low, actually the state or the process in this case. Okay, let's go ahead. The same goes to the triangle. It's just the replacement of this bubble or O letter. I'm not going to speak about it. It's the exact same thing. So what matters here is the active low at the input or the active low at the output. This is what matters. All right. The inverter operation, how does it do the job? So we said if you provide 0, it gives you 1 is the complementation process, or if you provide 1, it gives you 0. That's exact complementation. Why? Because we have only two possibilities. These two possibilities are 1 and 0 or 0 and 1. And in that case, we may have whatever input possible, especially in terms of a waveform. Then you need to see where it is low, it would be inverted to high, or when it is high, it would be inverted to low. All right. In this case, I have to explain about something we call timing diagram, and it's extremely important. We have a lot of questions about it. It is when you are given a waveform and you need to find the output, and this waveform is an input to a circuit. Multiple maybe waveforms we will see after a while. But for the inverter, since it has only 1 input, so we assume that we have only 1 input and we need to create the output diagram. How do we do it? We need to sketch like this dot line exactly with the edges of the input and see how the output reacts. Let's take an example here. For this example, we have this waveform. You see these levels, 1 and 0. When 0 is changed, we have an edge. Then you need to provide the dotted line here. Again here, 1 is changed to 0. Again here, 0 is changed to 1. Again here. Then you need to draw. Draw what? When the input is 0, that means the output is 1. When the input is 1, then the output is 0, 1, 0, 1, etc. This is exactly what we do. Be careful about the timing. This is what we need to have always set in a precise way. Otherwise, our drawing or the output of what we draw will not be accurate. Alright, so it's easy. I don't want to spend more time here. What happens is check the level. 0 will be 1, 1 will be 0. Just make your timing precise. That's it. Alright. For the NOT, NOT gate, how do we represent the output? The output, if the input is A, it will be negated, or it will be A bar, or not A, if you would like to pronounce it in another way. Alright. The next gate is AND gate. For AND gate, what we have is minimum of 2 inputs. Now for the inverter, we have only 1 input. We can't have 2 for NOT gate. It's not possible. If there are 2 inputs in NOT gate, which one will be inverted? Both of them. That means we are going to another gate, another type of gate. But for an AND gate, for the AND gate, we must have at least 2. It may be more than 2. That's possible, but not less than 2. So we have these 2 inputs. We may connect both of them to 1 input, that's possible, but that doesn't change the state or the fact that we have 2 inputs. Alright. So for 2 inputs, we have the symbolic diagram, distinctive shape. This is called distinctive shape, and we have the rectangular outline. For the rectangular outline, we don't provide 1, that's for NOT. Here we provide AND. Okay, the ampersand. We have A and B as inputs. They could be any other letters. It doesn't matter. And X as an output. It could be Y or any other letter. It doesn't matter. So we have something we call a truth table for this. But before we go to the truth table, we explained about this before. The output, the status of the output depends on the state or the states provided for the input. How many states do we have for 2 inputs? We need to apply 2 to power the number of inputs. 2 Y2 states, and how many inputs do we have? 2 to power 2, that means 4 states, 4 possibilities. If you have more than 2 states, if you have more than 2 inputs, you need to apply 2 to power, for example, 3, 4, etc. We will see. So this is the truth table of A and B only. That means 2 inputs, and in that case, what are we going to have? How can we cover all possibilities? We discussed this in discrete mathematics. For those who didn't take the class with me in discrete mathematics, no problem. In order for us to cover all possibilities, we need to list down all the distinctive or distinguished cases. 0 and 0, 0 and 1, 1 and 0, 1 and 1. All of them are covered. So 0 comes with 0, 0 comes with 1, 1 comes with 0, 1 comes with 1. Now, in order for you to cover all these cases, it's easiest to go 0, 0, 1, 1, or if you like 1, 1, 0, 0, then 0, 1, 0, 1, or 1, 0, 1, 0. It's up to you, but we usually, traditionally it's going this way, 0, 0, 1, 1, then the next one, 0, 1, 0, 1. You cover all possibilities in this case. All possibilities are covered. Now for the AND gate, what happens? If you have any or as 0 in the input, then the output is 0. Otherwise, it is 1. If all of them are high, otherwise always 0. So in the case of all high, the output is high. Otherwise, all of them are zeros. Now let's take the example of 3 inputs. How many possibilities? 2 to power 3. That is 8, and for 8 we have 8 states. How do I cover all possibilities? Go for zeros 4 ones, then 2 zeros, 2 ones, 2 zeros, 2 ones, then 0, 1, 0, 0, 1 until you reach the end. This is the easiest way. Alright, again the truth table, all are zeros except for all high inputs. It's extremely simple as is, but sometimes we get waveform. Now when we get waveforms, we need to have at least 2 waveforms, that means 2 inputs, and the output will be based on these 2 inputs. Now look for when both are high, because we have only 2. Otherwise, it is 0. So what we need to do, we need to sketch the timing diagram when they are both high and provide the output high. Now, you don't have to care about this. This one, you don't have to care about it. Just sketch where they are both high. Okay, now that's it. So we need to sketch from here. Okay, this is the first point. Both are high. This one is high. Oh, I'm sorry. This one is high. Let me take the pen. This one is high, and this one also is high. So sketch these two. This is high. You don't have to care about this one. 0 is guaranteed. Come here. This one is high. This one is also high. Okay, sketch. Take the timing diagram from the edges. This one is high. Then the rest, this is 0, 0. The rest is 0. Why? This has 0, this has 0, this one has 0, and that's it. Why you take a shortcut in this case? For just making your job easier and more quicker. Why? Because if they are not all are high, or not all of them are high, then take just a shortcut or a short circuit. It is immediately 0 or low. Sometimes the inputs may not be as clear as we think, so the timing diagram may not exactly match. Look at this example. If we think about this example now, look, the timing diagram, we have one here, high here, but it's not up until the edge here. We have until the side. So you need to place the timing diagram based on whichever edge moves from 0 to 1 or from 1 to 0. Here we have the movement from 1 to 0, so you place the timing diagram accordingly. Again, you do the same. Since you have 0 here, you don't have to care. Since you have 0 here, you don't have to care. Or low level. Again, the same low level here. So we have high starting from here, this edge. Start the timing diagram. We have 2 high here. It ends when this one goes to 0. Again, here we have 2 high, starting from this edge. All right. It ends here. Why? This one is going back to 0. And that is how you place this high state. So small, they may be smaller than what you expect. This is possible. There will be no problem. You just need to pay attention to when they are both high. No matter how small it is, I mean the pulse width, it doesn't matter. Okay? You need to pay attention to that. We may have more than 2 or 3. We may have 4 inputs. It doesn't matter. It will, all the outputs will be ANDed. It will be A and B and C, or A, B, C in this case. It will be just the AND operation. All right. OR gate, for the OR gate, it's the Boolean. It applies, or it creates, or it does the Boolean addition. The Boolean addition is exactly adding A and B, but in a Boolean way, which is ORing them. This is what we call OR. The OR gate itself is represented by this shape, a little bit curved from the input side, from the output side. This is the distinctive shape. If you would like to go and check the rectangular shape, you will find it this way for AND. It was with ampersand, this one greater than or equal 1. Well, this one is not popular, however, you may see it or face it, so you need to be aware of what it is, okay? Alright, the truth table for OR gate, let's take the simplest way, 2 inputs. It's exactly same like AND. It needs at least 2 inputs. So we have A and B, 4 possibilities, again 0, 0, 1, 1, 0, 1, 0, 1, and this is the truth table. I assume you guys are familiar with the concept of truth table. We explained about it before, yet we are revising it now. It doesn't matter. but just be careful about its state, why we are going to use it a lot in this course. Alright, so we have 0011, 0101, we covered all possibilities. Now for OR gate, there is only one case that it is low, when all inputs are low, otherwise it's always high. Okay, so that's what you need to pay attention to. Take a waveform. If you think about a waveform, what you need to do, you need to just look for the states when both of them are low, otherwise you don't have to waste your time. This is 1, ignore. This one is 1, ignore it. Don't even look at it. Okay, both are low, then yes. You sketch the diagram from here, low. Again, both are low from here, starting from here. Yes, you sketch it low. Otherwise, it is high, and you don't want to even spend time in checking it. Why? If any of them is 1, or both of them are 1, or all of them are 1, then in that case the output is 1. Alright, let's not spend more time here. Let's move. The waveforms may be a bit tiny or different in the timing, so you need to be careful. You need to be careful means what? Look when they are all zeros. So here, this one also, this side, again this side, okay, here again this side, and just set up your timing diagram in an accurate way so that you can easily find the output. Otherwise it's high. So my personal advice is, for AND, always determine the high state. Why? Because it may be the least. When they are all high, it may be the least of the possibilities. For OR gate, determine the low state. Low state may be the least, means when are all low. Okay. Now for OR, it's represented by A or B with this Boolean addition. It may be more than 2, 3, A, B, C, and will be just A or B or C. The same goes for more than that, and there is no point of the repetition. Okay, what kind of application? A common application for an OR gate. We can use OR gate for intrusion detection. Intrusion detection means what? Anything comes as high for this line makes the output high, right? It's like an alarm. For example, if someone is trying to open a door, if the door is closed, it's kept low, the input. If someone tries to open it, when it is open, it activates a state here with 1, and what happens? 1 or 0, closed, this one is opened, so it activated, the output will be activated, and at the same time the alarm will start the siren. Alright. And in that case, it has just a simple application like this. One of the applications, usually in reality it's much more complicated than that. However, it's possible to design in such a way. A NAND gate. NAND gate is actually a combination of what? Combination of not AND. It's the negation of AND. So we have an AND gate which is negated. AND gate with not. All together we call it a NAND gate. A NAND is one gate. You don't have to think about anything other than being a gate with a specific states. Alright, and a NAND gate is exactly AND with minimum 2 inputs and an inverted output here or a bubble here. Alright. How about the truth table? It's a negated AND. Now the AND, if you remember, it's only high when these two are high, otherwise it's low, and for this case what we have is exactly the opposite, the negation. So it is 0 here, 1 otherwise. If the inputs are not all high, then the output is always high, otherwise it is low when all the inputs are high. Alright. So for NAND gate, you look for what? You don't look for all these states, you look for when they are all high, opposite to NAND. Look at when they are all high, set up your timing diagram, this state, this part, okay, both high, this part, here no, here no, here no, so this part, and finally this part. When they are all high, the output is 0, so you list down 0, otherwise you just connect them with high state. Alright, how do we represent it? It's not AND, so A and B negated, or the complement of A and B, not A and B, the complementation of this process. According to De Morgan's law, if you remember from discrete mathematics, if we apply the negation of A and B all together, the negation of all of it, what happens? It's exactly equal to the negation, the ORing of their negations means what? This is equal to A, not A, or not B. I'm not very talented with writing with this mouse, so please forgive my bad typing here. It's exactly equivalent in this case. It would be the ORing of their separate or distinguished negation. And what this tells us? It tells us that I can replace an AND gate with what? I can replace it with a negative OR. This is another type of a gate which is equivalent to a NAND gate. They are not equal, of course, because the implementation is different. However, what is equal is their outcome here. Why? It's exactly not A or not B, or what you see in this truth table, negative OR. So if you find negative OR, it's equivalent to NAND, remember it. Alright, so we have a negative OR with 4 inputs. What will be the output? Look for the all high state where it will be low, otherwise it will be high. You can do it on your own. I don't have to do it for you. Just look for the states, sketch the timing diagram. You just need to be careful with this while solving. That's it. All right. We have a NOR gate, which is actually a contraction of not or short form for not or, a negated OR gate. So it's an OR gate with a negation at the output. Okay. Or you can provide it with the rectangle outline, like just a rectangle with one greater than equal 1 and a rectangle at the output. All right. The same idea is the negation of OR. So the negation of OR is always low unless or except one case when all inputs are low. All right. Why OR gate is always high, the output of an OR gate is always high only in one case, when all inputs are zeros. This is the exact opposite, or the inversion of that process. It's always 0 except while it is high here. Alright. So the output of a waveform, you just need to set up the waveform. You can look for when they are all zeros, otherwise the inputs, otherwise the output will be 0. Now let's look for zeros here. And this is high, ignore it. Zeros again here, this part. This one high, ignore it. Zeros again. Here high, ignore it. Both are high or one is high, it doesn't matter. These are zeros. So it will be here high, low, high, low, high, low, high. All right. Okay, for the NOR gate, we can replace it by another gate. We call it negative AND. Now remember from also the De Morgan's law. I have not explained it in logic circuits, but I explained it in discrete mathematics. De Morgan's law states that the negation of an ANDed or ANDed terms is actually the ORing of their separate negation. And also we have another one, that's the first one. The second one says that the negation of an ORed or ORed terms is exactly ANDing their own separate negation. So we have A or B negated. What will be the output or the outcome? The outcome will be the negation of their own ANDing process. Not A and not B. That is the negative AND, and it gives you the same exact outcome here. Alright. The same process, if you have more than 2 inputs, you have to apply them the way they are. And what you are looking for here, look for when they are all zeros. If you look for all zeros, you will get it high. Otherwise, it's always 0. Alright. we have the exclusive OR. The exclusive OR is exactly applying the addition of modulo 2, or the the Boolean division. It's the module 2. The module 2, you guys are familiar with it. It's the remainder of the division by 2, and that's the exclusive OR. It's an OR gate exactly, but with just one curve covering the inputs, and that's the exclusive sign. It's referred to by plus with a circle telling that it's an exclusive or XOR process. Okay, in the rectangular shape or outline, it's not greater than equal, it's directly equal to 1. And I will tell you why we say equal to 1. Now for the exclusive OR, the process of it is actually sensing if the levels are same. Levels are same means what? Either they are both zeros or both ones. It doesn't matter if they are high or low. When they are same, the inputs are same or at the same level, then the output is 0. That's how it senses it. If the inputs are not at the same level, 0, 1 or 1, 0, then the output is 1. It takes it exactly the opposite way. If they are same, the inputs are same or at the same level, the output is 0, otherwise it is 1. Alright. Now, we have another gate also, we call it the exclusive NOR, yes, XNOR. Is the negation of the OR gate. Negation of an OR gate is NOR, but we have an exclusive type which is called exclusive NOR, XNOR. So this one, I said it, I think, yeah, XOR. We refer to the exclusive OR, XOR. And for the exclusive NOR, we refer to it by exclusive XNOR. Okay. Now, what's the idea? The idea is like same. It's XOR, same, but with a negation. It's like a NOR gate, but with exclusive process. Exclusive process here, what? The negation of the XOR. How do I know the output? Now look, the output here is 1 when they are different. Now it will be, the exclusive NOR will be 1 when they are same. So it will sense if they are same, the output will be 1. Otherwise, it is 0. It's the exact opposite. Alright. Now, it's just the negation of the XOR. So we have either a bubble here or a triangle at the output. Okay. This is the truth table. It's exact opposite. Here are zeros, and when they are both zeros or both ones, the inputs, the output will be 1. Alright. Now for XOR, XOR can be represented by A not B or not A B. How do I know? I'll teach you when we reach to Carnot maps and the conclusion or the extraction of expression from truth table, but I can explain it to you here quickly. Let's say we look for the high state here. What's composing it based on ORing terms? Okay. Now look at this. If I put this one not A, it will be 1 and B. So not A and B will guarantee 1 for me. A and not B will guarantee also 1 for me. Sum them up. That means all these terms, not A and B, or A and not B. That's how it is found. I'll explain it later on, but just to give you an idea, not to be puzzled, how did he get this one? He didn't explain it to us. All right. A not B, or not A and B. If you say this one at the beginning, it doesn't matter. It's fine. There is an associativity in this case. We can shuffle them. There is no problem. For the XNOR, it's provided A and B, or not A and not B. How do I know? Now look at this. Not A and not B, first high state, and then or A and B. Alright. You can start by this one or start by this one. It doesn't matter. Alright. Now, how can I prove it mathematically? Okay, or of course we speak about Boolean algebra, not normal mathematics or arithmetic. if I negate this term, now look, A not B or A and B. If I negate the whole term, again, to De Morgan's law, the negation of two OR terms, we have two OR terms, A and not B, or not A and B, we have their negations here. All together, it would be the AND of their own separate negation. Again, apply the same process. We have two AND terms, which are negated. It will be the negation of their own ORing. Now, double negation takes you back to the same variable. Double negation takes you back to the same variable. All right. Now apply ANDing. So just distribute A bar A, A bar B bar, B A or A B. We say it A B or B B bar. Now this one is 0. You remember when you AND a variable with own complementation is always 0. This one is also 0. What's left? A bar, B bar, or AB, and that's it. All right. So this is another application for an XOR gate. The XOR gate can be used for logic addition. For the logic addition, which is the type of XOR somehow. How do I know? Now look, 0 0 is 0. 0 XOR 0 is 0, 0 XOR 1 is 1, 1 XOR 0 is 1. How do I know they are not, the levels are not same here? How about here? 1 or 1? 1 or 1 actually is 1 0. So we say it is 0 because the levels are same. 0 with 1 carried. With 1 carried. Alright. The last part, this part is a bit more of theory, but it's important for you to understand it and learn it. Now we have something we call it programmable logic. We explained about the concept of PLDs or programmable logic devices, and we said that we can create it by an AND array. So we have an AND array, and this array, we can compose some connections or create some connections to program it. So in order for us to program this kind of a gate, we need to create, make or break some fuses or links. What am I saying? Now let me show you here directly. Now look, usually we get an array like this. Why do we say array? What kind of array are we speaking about? Look, we have like a net, a whole net of connections. All together, they may come all connected at the beginning. So what we need to do, we need to just break these and keep the ones we are interested in. These are programmable links. So what we do in our programming of these gates, the output here, actually, at one side we have the output, and at one side here we have the input, and all this network is programmable. Now, in order for us to program it, we need either to keep this connection or remove it. Now look, if I want A and B for X1, I need to keep only A as an input for this one. Now this one is gone, this one is gone, this one is gone. Only B kept for one input, and A is also kept. The rest are all removed or broken, in other words. All right. We do the same if we are looking for A bar B or not A B, then we will have to keep not A. Now, how do I keep it? Keep its link and remove the rest. This is not done manually. There is no such thing. You do it by your hand. It has its own process. I'll explain about it in a while. Now, keep also B. Look at this. If we are looking for A and not B, well, this is A, keep it. How do I know this is A? It's A. See this connection? It's A. How about B bar? This is B bar. So A and not B bar. All right. And this is the process. If I give you a question like this, you should be able to get these outputs, because we have an array, so we expect different outputs here. The first one, A and not B. The second one is A bar and B. The third one is A bar and B bar. That's it. All right, how do we do it? So you said to us theoretically how this thing is done. We have different technologies. We have the first one, you can say the eldest one, or the original actually type of technology called fuse technology. Fuse actually exactly fuse the way you understand it. Some metal part that we can break by some certain current. So these links here we have are composed of some metal that we can break by passing some high current inside of it. It will just burn. And in that case, we will lose the connection. We will lose it permanently. So once you design it, program it, it's done. You can't change it. It's just designed once. So you have to decide from the beginning which links you are going to keep for your own outputs here, and later on you can change. You can just buy another one and reprogram it or program it the way you like. All right. So now, what is it used for? Usually for the simple, actually, programmable logic controlled logic devices, and it's until our today's technology is being used. It's common. It's actually not expensive, inexpensive. And it is usually used for small circuitries, not very complicated ones. How do we do it? As I said, we just pass a high current inside this fuse, and what happens is just the diffusion or the break of this link in between, and that's it. And as I said, it is done one time, so it is one time programmable. Once you program it, you can't reprogram it. You can't create this link again. It is done. It is burned. You can't regenerate or create that type of connection. We have the other way. We said either make or break. So we studied about the breaking a fuse. How about making the connection? This is what we refer to by an entire fuse technology. For the entire fuse technology, is exactly the idea of creating a link or a connection between the points that we have. So we have here connections. This one will not be composing a real connection until we diffuse it. If we diffuse these parts, we create the connection. This is what we call anti-fuse. Instead of fusing, actually we diffuse it. We create the connection. That's what it is. What it means. How is it done? How it is done? It's done simply by having like some you can say plates, and these plates, between them there is some insulator, and this insulator has some characteristics. When we apply high voltage between these two plates, what happens to the insulator inside diffuses and becomes some sort of conductor. And that's exactly how it is done. Now look at this. We have the contact plates here, and we have an insulator. If we apply certain voltage between, this one diffuses, and what happens? We have a conductor. All right. And this is also done one time programmable. Why one time programmable? Once you do this, once you create the connection, you can't take it back to its insulator state. It's already done. You can't reprogram it. We have another type of programmable technology, which is the EEPROM. The EEPROM is electrically programmable read-only memory. You know the read-only memory, the ROM. It's very popular in computer and computing applications, and this one is based on some type of programmable device that we usually program once unless it is reprogrammable. For the electrically programmable read-only memory, we can reprogram it, yes, but with some specifications. However, for the time being now, the electrically programmable read-only memory, this type, the specific type, we can't exactly reprogram. We program it one time, and if we want to, well, you can say erase whatever available in it, we need to go to some specific type of laboratories where they apply ultraviolet light to the PLD itself to remove whatever programming available in it. And that's not easy, neither easy nor is it expensive. Is it cheap? All right. How this technology is done, what type of possibilities we have for opening or closing, making or breaking of links. Now let me show you here directly. I'll explain all these things here. Now this is what we call MOS technology, metal oxide semiconductor transistor. You don't have to know much about it. What you need to know that it is a transistor that we can make it as a switch. So you don't know what transistor is? Fine, no problem. Imagine it as a switch, and this switch can be turned on or off. Now look, we have the high voltage connected directly to an NAND gate from here, and then we have what? We have one part here, for each connection from A bar, B, and B bar, connected with a transistor. So what does it mean? Now A will be able to activate the transistor to turn it on or off based on its own state. If it is 1, the transistor will be 1, and this output voltage will be connected to low ground. And what happens? The input here also will be connected to ground. Okay? Or in other words, it will just display the A state itself. Otherwise, it's always connected to high. Wouldn't change the other part. Why in AND gate, if you connect any input to high, it doesn't change the state except based on other variables. So what we do, we're looking for either opening the switch by the state of the variable or closing it, 0 or 1, depending. So either permanently programmed to off or permanently programmed to on, depending on your own combination. If you are looking for A and B, you keep A and you keep B. So you turn the transistor on and you remove these high voltage. As they are high, they wouldn't change anything in AND. What we are not interested in them, we are interested in B directly. So the connection will be like this. Now look, it's like this. This is B, and A, it will be like this. So what we are taking, this is of course virtually, not exactly in reality this way, but this is how it is symbolized. All right. How it is done, you don't have to worry about the floating gate transistor, how it acts and how it is done, what kind of mechanism we use. You don't have to worry about those really, but you need to understand what I said here about how we create on and off and get the variables based on that. All right, I explained about this, I explained about it, on and off, and how the output is based on the transistor. We have the electrically erasable programmable read-only memory technology, and this one allows you to program it usually in system programming or even by some circuit board technology. It's possible for you as a programmer to do it without going to specialized laboratories to do that for you. So that EEPROM, or sometimes they write it E squared PROM or E squared CMOS. CMOS also one type of metal oxide semiconductor, the complementary type. You don't have to worry about what it is. It uses the same technology, the floating gate transistor. Do you need to know about this one? Unless you are interested in learning about it, you can search. Otherwise, it will not come to our own exam as a detail. Just as a method, maybe I would ask about the EEPROM itself technology, how it is done. How is this one done? It is done not exactly like this by a switch directly with a connection. No, rather we turn on and off this transistor based on the input we provide in the cell itself, and we can reprogram it ourselves. We can reprogram it. It doesn't need the ultraviolet specialized fixture or laboratories, and in that it is more common. It is more useful for us programmers. How about the flash technology? We all use the flash, the pen drives that we use, and this kind of technology is quite popular. It is based on the EEPROM technology. The EEPROM technology is designed, as I said, based on the memory cell itself. We activate the transistor based on the memory cell. How do we do that? I will show you in a while. Just hold on for a few seconds. Usually, for what determines the flash technology itself is that it is non-volatile. It keeps your memory. It doesn't lose it. Plus, it is reprogrammable. We can install data again and again in it. Okay, how about its capacity? Usually is big. Okay, it has a large capacity. We can store a lot of data in it, depending, of course, on the size. As extremely practical, it comes by small size flash drives, and that's why it's extremely popular. The price is also somehow affordable. That's why people use it a lot. All right, we have the static RAM. Now RAM is random access memory and usually doesn't hold the data when we switch off our devices. And this for the static RAM technology usually used for both actually FPGA field programmable gate arrays and the complex programmable logic devices. It is very similar. The concept is very similar for the static random access memory. Why static? Static in this case we refer to the way or the mechanism of its own programming. It's not dynamically done, it's statically done. All right, I'll show you how we use a memory cell to do this for us. The memory cell does what? If we activate the memory cell, we provide in it one, it activates a transistor or it turns a switch on. Transistor here means what? Switch, literally means switch. Now look at this. A static RAM cell, we can activate a switch to turn it on and A will be taken to the input, or we can place it off and this A will not be there. And that's how we refer to, if we are looking for A and not B, so this one would be activated and this one would be activated, the rest would be zeros. How? If you provide 0 here to the gate of this transistor, it would be off in a simple, just simple words, and they will be opened, all of them, except for these two. We provide 1 in this static RAM cell and we'll keep the connection on, and that's it. So it is like an on switch versus an off switch with 0. As easy as is. I don't want to go into the deep details that you guys will not need. All right. So now for the static RAM, it is volatile. Volatile means what? It doesn't keep the data in it. Why it doesn't keep it? It needs the electric supply and the state of the computer on. Otherwise, the data will be gone. And what you can recover is only just artifacts of the data later on if you want to analyze it. But you can't get your data again from the RAM. So in order for you to program it, you need to keep your program loaded somewhere in a permanent memory or a memory that can keep it. Then you load it into your device, whatever technology uses the SRAM, whatever, PLD or whatever, that uses the static RAM technology, in order for you to allow it to do, like exactly what we have in our RAM. It loads every time. It loads the BIOS, for example, or whatever needed for your device to start up. Every time it loads it when you start your own PC. Why? Because it doesn't remain in the memory, in the random access memory. When you stop or when you switch off your device, it needs to load it again, and that's what's meant by loading the operating system, loading whatever data, and so on. That's exactly it. This is it for the for this part, the second part. We are done with chapter 3. I tried actually to create quizzes, but we had really simple chapters. Now expect from me this weekend actually assignments for the 3 courses I'm teaching: the logic circuits, discrete mathematics, as well as programming languages. And starting from next week, I'll plan with you about our live sessions and the quizzes that we are going to have within the semester. Until further notice, have a good time. Goodbye.